Okay, we're talking about centripetal force here. Centripetal force again means center seeking, so it's important to understand that that's what we're talking about. We're talking about a force that's directed towards the center of the circle, and of course it's force, so it's going to be in newtons. And remember, if you have a net force, you're going to have an acceleration. And when something's moving in a circle, it is accelerating even if the speed is constant. So if I'm moving around in a circle at a constant speed, the force is accelerating. So let's say, for example, that's me. This is an overhead view, and I'm whirling, I don't know, some type of ball on a string around in a circle like this. Which way is the centripetal force directed? Right. The centripetal force would be towards the center of the circle. It's going to give you a net force in that direction, even though the velocity is tangential to the circle at that point in time. That's kind of important to understand. Now let's go through equation-wise. The centripetal force is equal to mv squared over r. Really, that's nothing more than m times centripetal acceleration. Centripetal acceleration is equal to v squared over r. So you can be moving at a constant speed and still accelerating. It's important to understand that. The other thing kind of important to understand is the fact that it's not really a force by itself. Centripetal force is caused by something else. It's not something that stands alone. It's something I need to solve problems in which things are moving in a circle. But it comes from something else. It could be tension, as in the example above, or me swinging my sister around in circles by her arms when we were kids. It was the tension along my muscles that were causing it to happen. It can be gravity or weight. The moon stays in orbit because of the gravitational attraction from the Earth. It's kind of important. It can even be friction, and probably the most common place we see that is driving a car. When we turn the steering wheel in a car, what we're doing is redirecting friction towards the inside of the circle, excuse me, and therefore we accelerate and turn the corner. So that's kind of important by itself. Let's take a look at one practical example of it. So hold on just a second. I'm figure this out. Let's take a look at this.
Face the back of the circle, weight evenly distributed, and your feet shoulder width apart. The discus should be held in your throwing hand with your fingers spread. After a preliminary swing or swings, you should transfer your weight over towards the left side as you turn in an anti-clockwise direction of the ball of the foot. The wide sweep of the free leg assists in balance and drive across the circle. The movement of your legs is accelerating, and the throwing arm is left behind, although it remains active. You create a wound-up posture with your hips in advance.
Okay, that's the key thing that you want to see right there, is when the discus thrower actually lets go of the discus, he lets go of the discus when it's off to the side, and that's what powers it down as far away as possible. He wants to generate as much speed as possible in his spin, and speed actually is the key thing. So energy. Let's numerically do a sample. Let's say, for example, that I have let's say a 2,000 Newton car, and it's driving at 4 meters per second, and it rounds a curve of let's say 8 meters. I want to know A, the mass. I want to know B, the acceleration, and I want to know C, the net force on the car. So let's go through and take a look at that. First of all, the mass hopefully is pretty straightforward, that's going to be 200 kilograms. You can use 9.8 if you want and get a more exact number than that. That's okay, either way you understand it. So that's part A. The reason that's important we'll see later. Even if they don't ask for that, you're going to have to do it. Now for part B, I want to find the acceleration. Well, since you're rounding a curve the key thing, centripetal acceleration, comes into place. So v squared over r. Now if we plug and chug, we go 4 meters per second squared divided by 8 meters. 4 squared is 16. 16 divided by 8 is 2. Now if I take a look at the units, I'm going to have meters squared over seconds squared divided by meters. I get meters per second squared. That's an acceleration unit, so I'm probably right. For part C, I now want to say that centripetal force, well, we know that it's a net force, and we know the net force equals mass times acceleration. So here's a shortcut. 200 kg, that's the reason you needed the mass earlier, times an acceleration of 2 meters per second squared gives you 400 newtons of force to turn that corner. Of course, I can also do this. I can also say, since I know it's moving in a circle, it's mv squared over r. Move that up where you can see it. That it's mv squared over r. I can also go in and say 200 kg times 4 meters per second, that quantity squared, divided by 8 meters. And again, if I do that, I'm going to get 200 times 4 divided by 8. Hey, it's equal to 400 newtons again. Well, let's take a look at the units to make sure it's newtons. I have kilograms times meters squared over seconds squared divided by meters, which reduces to kilograms times meters divided by seconds squared, and that's a newton. Remember, with centripetal force, it's a force that's acting towards the center of the circle. Anytime I see something moving in a circle or part of a circle, I'm going to need to encounter that, such as going around a Ferris wheel, turning a corner in a car, a kid on a swing, and that's a common theme that they've used a bunch of times on the AP test in years past. I hope this helped.